Okay, in this part of the lecture, I'm going to leave the random generation example behind. I'm going to look at some different examples based on expressions. So we'll move from high school to late high school expressions. The difference being that we're going to look at expressions which have variables in them, symbolic expressions. So what is a symbolic expression? Well, as I said, the only difference that I'm interested in here are expressions which have variables, x, y, z, whatever. Okay. So we're going to add an additional clause to our expressions, and that clause will represent variables. And how will we model a variable itself? Well, there are many things we could choose, but I'm just going to choose a string. So the string will just give the name of the variable. Okay. And we can derive EQ. And here's some examples of expressions. So we want to do y plus 2 multiplied by x. That's one of those things there. Let's throw a couple of examples in that could be useful later. Okay. So no real big surprises there. We now need to go in and modify some of our definitions. So let's start by giving an example. An example of a function to compute the variables that are contained in an expression, and the variables will be returned as a list of strings. So, for example, the variables of this guy will be y and x as two strings. This one also has two strings, and this one has the empty list of variables. Okay. So how many variables are there in a num? There are none at all. How many variables are there in a variable? There is just one. It's s. How many are there in the add expression? Well, it's whatever the number of variables in E1, and we need to join them together with the variables of E2, and we're using just a list here. So we've got repeated elements. If we wanted to avoid repetitions, we could use the function union that we saw previously from data.list, which will add the elements of the second without any duplicates. Question?
Plus adds two lists together. Right?
It joins two lists together indeed, yes. And this one, this case is in fact exactly the same, so it's rather tedious. Now, you might think at this point, because these two cases are exactly the same, you might be tempted to say, okay, let's make this a pattern match. And then we don't need this definition down here, because we just pattern match on any operator, and then we just join them together. That looks nice. Unfortunately, we can't do that. We can't do it because the operator is a function, right? Num is a function. Add is a function. They're all functions. And if we were to pattern match on a function, then the definition and the implementation of that will somehow have to match whether it's the same function or not, if it's going to be truly functional. You'd either have to say whether it's the same function or is it the same pointer to the function, or I don't know. There's no good mathematical justification for pattern matching on operators, so or functions of any kind. So quite simply, Haskell doesn't allow that. Again, if we wanted to fix this, we should have fixed it already in the definition of the data type. And then we could have had an operator being just an element of a enumeration type as a parameter to the definition of an expression. Question?
Yeah, here we can just use an underscore, right?
No, because an underscore is also pattern matching on the operator. So logically speaking, you're quite right. The underscore could be a special case because you don't have to look at it. But unfortunately, that's not allowed either. So you could imagine extending it so you could do that special case, but no, afraid not. So we have to have the two cases here, even though they look painfully similar, and that's the variables. So we can ask what the variables of example 1 are, and they're y and x. And for example 3, there are no variables at all. Okay, so that's kind of obvious. Eval, now, what do we do with eval? Well, we don't actually have to do anything. Eval could, if we want something of this type, it's integer. If we wanted something of this type, then we could define it with these equations, and if we apply eval, then we can eval ex3, and it works. And if we try and eval ex1, we get an exception. It goes wrong because we don't have a case for var. We could of course eval with a var x and give an error message. But actually what we're going to do is something different. We're going to actually change the type of eval. If you want to evaluate an expression containing variables, you have to know what the values of the variables are, right? We want to use an expression to represent a function, x plus 2. If you want to work out what the value of x plus 2 is, you need to know what the value of x is. So if we have a table which tells us what the values of the variables are, then we could give a sensible definition of eval. So we could take something of this type, where table is just a shorthand. It's a shorthand for what's the simplest way of representing a table of things. Well, it's to use a list of pairs of the thing you want to look up, which is a string in this case, and the value of that string, which is an integer. So the simplest notion of a table that you could come up with in Haskell is just a list of pairs, the key and the value. Okay? So if we had such a table, then we would be able to define eval. So eval given a table and an expression, but equal to eval prime of the expression. Let's make this guy eval prime. So this thing is now a helper function to our main function, because the table never changes. The table is fixed. So I'm just changing all these to primes because they're the helper function. They don't use the table. But they can use the table whenever they need it, and they'll need it in this case. How do you evaluate a variable? Well, you need to look for the value of the variable in the table, and the t is the table. So we need to define our function look. So the function look will take the key that we're trying to look up and a table, and if it doesn't find it in the table, if the table is empty, for example, then we've got no choice but to give an error. Okay, so we've got no value for the k. Otherwise, how do we look up a key in a table which looks like this? Starts with some key prime and some value, and continues with the rest of the table t. So this is a table whose first pair in the table is this. What do we do? Well, it depends. It depends whether this k and this one are the same. So if k is equal to k prime, then we've found the value. It's v. Otherwise, it's the result of looking for the value k in the table t. That's the rest of the table.